formula of organic compounds. So in the last class, we met just a general thing of what organic compounds are, and we noted that these organic compounds tend to have carbon, hydrogen, and oxygen as the main elements in the compounds. Now we're going to look at what different compounds are formed based on how bonding takes place. All right, so these compounds are actually placed in different groups. All right, now we're going to explore three types of formula. We're going to explore the molecular formula. So a molecular formula is what you are used to. So if, for example, with methane, right, we say methane is CH4. So a molecular formula, ladies, is what we are used to. So we're going to explore the molecular formula for organic compounds. We're going to look at the structural formula. So structural formula is what you see here, where you are drawing out the structure now. What is it that it looks like? Instead of just writing all the elements involved put together as one, you're going to now draw it out using sticks in between to represent the bonds. All right. We're not going to do ball and stick model, unfortunately. So the ball and stick is like a kit. If you want, you can explore it by using Play-Doh and matches stick, or they actually have a kit called the ball and stick kit, right? So you can explore that. And we're going to look at condensed formula. All right, so three different formulas that we're going to explore. So before we explore that, we need to know what are these groups. All right, now the groups based on how bonding occurred is known as functional group. So a functional group for an organic compound, ladies, pretty much defines, it's the identity of the compound. It tells you what group you belong to. So if you can identify a functional group, we can actually classify organic substances. All right, so it says that a functional group is a particular atom or a particular group of atoms or a particular bond between two carbon atoms within the molecule. So we're going to look out for three things. Either there's a particular atom there that is going to be the distinguishing factor, or there are a group of atoms that's a distinguishing factor, or you're going to have a particular type of bond. So whether we have single bonds, double bonds, or triple bonds. So these are distinguishing features. So every molecule that is in that particular group will have this functional group, right? Now, that particular group that I'm talking about, right, I refer to it as a family. And this is known as your homologous series, all right? So your homologous series, ladies, I look at it like family and members of family. So your homologous series will be the family. All right, so whether you had, let's use you as an example. So you have the Hunter family, you have the McDonald family, right? Now within your family, there's going to be distinguishing characters, right? So sometimes in a family, Liz, you look and you say, boy, everybody have the same fingers. The fingers all look alike. And you've heard that before growing up. They probably say, boy, your eye look like your mother own, or your fingertip look like your grandfather own, right? So you find that within this homologous series, within this family, we have distinguishing characteristics, all right? And that is the one that is setting them apart now is the functional group. So we have the homologous series, which is the family. And within the family, you're going to have a particular trait. That particular trait is your functional group. All right. So for example, let me just give you an example here. If we have this functional group here where you have carbon single bond carbon or carbon double bond carbon. No matter how many carbon atoms that are in the chain, you are going to find once you have a double bond between two, it belongs to a certain group, right? So these are all the functional groups here. So everybody in the family is going to have this particular group in it, right? And the family groups, we're looking at alkanes, alkenes, alcohols, and acids. Later on, we're going to be looking at esters. So we're going to utilize this table here. We have two tables. We need a table with prefix. That is what is going to give us now a specific name for the family member or the organic compound. And we're going to use this big table here, right, to actually come up with the formula, the different formula and the different names for the compound. But let's look a little more at our homologous series. All right, so your homologous series, ladies, because you have these organic compounds in this family group, what happens is that they display similar characteristics. So it's almost like when we're looking at periodic table. In the periodic table, you had groups, right? And the groups were also called families. And what you find out was that members of that group, right? So members of that group would have exhibited similar properties. So like members of group 1, all of them were reactive. They all had a single electron on their outer shell. They were soft metals. So they displayed similar characteristics. It is the same thing now for your organic compounds, all right? Once you're in this homologous series or this family group, you're going to have similar characteristics. So pretty much, let's run through them. The first one is that all members in the same homologous group has the same functional group, all right? So you have the same trait. There's a particular trait you have and everybody has it. So that's your functional group. So if all of them have a double bond, right, you're in the same homologous series. Members in the same homologous series will have the same functional group. That's the first one. Second one, all members in the series can be represented by a general formula. What does that mean? It means that to get the molecular formula for these individual members, right, there's a general pattern that is followed. And that's what we're going to look at in a minute. All right. It says each member of the series differs from the member before or after by a CH group, right? So it's like us saying you differ by plus or minus one. They are differing by CH2, right? A carbon and 2 hydrogen atoms. All members of a series possess similar chemical properties. Reactivity decreases as molecular mass increases. So depending on the formula for each individual member, the more you have your molecular formula or molar mass, remember how we find that out? So you add all the mass of each atom in the formula. The more you have, the more mass you have, is the less reactive that you are. All right, next one. All members of a series show a gradual change in their physical properties, meaning they are probably going to move from solid to liquid to gas. All right, so pretty much carbons. So when we have compounds with carbons 1 to 4, these tends to be gases. They're gases. So if I have 1 to 4 carbon atoms in my formula, right, then I'm a gas. If I have 5 to 15, I'm a liquid. And if I have 16 or greater, then I am a solid. So the state of physical state is going to change. right? The melting point changes. So the greater the molar mass, the higher the melting point, boiling point, and density. And you can see why. Because if my molar mass is increasing, it means that the number of atoms that are being bonded are increasing. The more bonds I have to break, it is the higher that my boiling and melting points are going to be. The more atoms I have, it's the more mass that I have. More mass equals more density. I'm going to be heavy. All right, so let us get to naming now. So to name a particular member of a homologous series, we use prefix. Now the prefix just highlights to you how many atoms are in your chain. So remember, you're gonna have carbon atoms bonded together, right? And if we do not have it branching off, then we call it a straight chain because it is one carbon following after another. So carbon, ladies, form the backbone of your organic substances. All right. So carbon forms the backbone. You're gonna have in a series carbon atoms bonded together, and then around the carbon atoms is where you will have either the hydrogen or the oxygen or other atoms bonded, right? So around it, around these bonds going around it, you will have your other atoms bonded. But your carbon, depending on how many carbons, even if it's 1,000 carbons, ladies, right? It is normally bonded to another carbon atom. That's your backbone. So let's go. If my member, so let's say my organic specific family member, the specific organic compound has one atom, then we use the prefix meth. All right. If it is two, we use F, ETH. If it is three, then we use prop, PROP. If it is four, then we use but, five, pent, and the list goes down. Now, what you're going to find is that these organic compounds, they're going to start off with this prefix here, no matter the family group that you are in. Now, you probably wonder, how is it that you're going to differentiate with these different family members if all of them pretty much, if member of family A has one, then the first name is meth, and member of B is only one, is meth again, right? How is it that you're going to know the difference? The difference comes in the ending. All right. So when we're naming our organic substances, ladies, it is just like when you're naming human beings, you're naming kids. There's a first name and there is a last name. The first name is the prefix, right? That's the first name. The first name is a prefix that is in the table. One is meth, two, S3, prop, four, but. The last name is the family name ending. The last name is the family name ending. So for example, we're going to learn about the big family group called alkanes. All right, so the family name ending for any alkane is ANE. All right, or ANE. So what you're gonna find out, just like how you can say, okay, Browns. So in the Brown family, everybody's last name is Brown. In the alkane family, everybody's last name is ANE, ANE. What is your first name? If I only have one carbon atom, then I'm going to put the prefix. And the prefix is METH. Member of the ANE family has two, I'm going to have the prefix ETH, but the ending, I must have my family ending, which is A-N-E. So put it together, I get ethane. Family group that you need to learn, ladies: alkanes, alkenes, alcohol. So these are organic alcohols now. And another name for it is called alkanols. All right. And we're going to look at acids. So they call them alkanoic or carboxylic acids. So these are the big family groups: alkane, alkene, alcohols or alkanol, acids, alkanoic acid or carboxylic acid. So whenever you hear them speak about carboxylic acid or alkanoic acid, they're speaking about organic acids, all right? So remember, we learned acids earlier. We learned that you had mineral acids and you had organic. The mineral acids are your hydrochloric acid, sulfuric acid, right? Your organic acid now. So when we spoke about citrus fruits having citric acid, that's an example, a specific example of a carboxylic acid. All right, so how are we going to do this now? We have a general formula. We have lots of things to practice with this table, right? So we're going to have a little fun. We have a general formula. All right. We have the functional group, and we're going to need the functional group when we start drawing our structural formula. But we're not going to start that until tomorrow. We have how to name it. See it here? So you have the prefix and the ending for the family name. So for alkanes, my ending is A-N-E. N. For alkenes, my family ending name is E-N-E or EN. Alcohols, I have anol. So all of them are going to end with anol. My carboxylic acid all will end with anoic. So you remember you asked about ethanoic, right? Look on it. Let me split this up for you now. So let's break down ethanoic. So ethanoic has ending. The ending is anoic here, right? So if this is anoic and the prefix is eth, how many carbons are you expecting in ethanoic acid? What we're going to practice today, ladies, right? We're going to take the table one at a time because it's a number of elements to it, right? We're going to have to learn to come up with the formula, but we're not doing that as yet. We're going to have to learn to name the compounds. We're going to have to learn to write the molecular and condensed formula, and we're going to have to learn to draw the structural formula. So we're going to take them one at a time. All right, so let us start with the simplest of them all. We're going to start with naming the compound. So I'm going to tell you how many carbon atoms and the family group that I'm going to refer to. You are going to tell me the name of the compound. All right. So I'm going to tell you the number of carbon atoms and I'm going to tell you the family group. You are going to give me the name based on this table here. So this column, naming, you're on naming. All right, so let's start. The first one that I'm going to throw out is an alkene with, or do you need, so the prefix is here. Take another look at the prefix. One is meth, 2S, 3 pro. All right, so let's go now. I want you to name an alkene. What's the name of the alkene that has 6 carbon atoms? Very good. Hexene. All right, what's the name of an alcohol that has 3 carbon atoms? Name propanol. Very good, propanol. All right, the name of a carboxylic acid with 4 carbon atoms. Ethanoic acid.
Bute.
Yes. So they pronounce it butane, an alkane with 5 carbon atoms. So pentane. Excellent. All right. Are we getting the gist of how to name it now? So in alkanes, we can have methane, ethane, butane, propane. In alkenes, same thing. We can have propene, butane, alcohols. We can have propanol, butanol, ethanol, the carboxylic acid, ethanoic acid, um, butanoic acid, propanoic acid. So it is quite general because all of them will have the same prefix, right? Depending on the carbon atoms, but the endings is what defines them. All right, now we're going to move on to using the general formula. So we're going to use a general formula to come up with the specific molecular formula for some carbon, some organic compounds. All right, so let's go with alkanes first. General formula, ladies, the general formula for an alkane is CnH2n plus 2. Let's see if I'm correct. CnH2n plus 2. All right, now it works just the same way like math. So N is the N will be the number of carbon atoms. N equals the number of carbon atoms in the chain. So we can pick up some random ones now. So let's start with meth, which is methane, right? Because I have METH, I know I have one carbon atom. So it means then my N is going to be equal to 1. What am I going to do? I am now going to try and plug this into my formula. All right, so I'm writing back my general formula, CnH2n plus 2. I need to now substitute what my N is equal to. So I'm substituting N into my formula here. So I'm going to end up with C1H, right? 2N, which is 2 times 1, plus 2. All right, so I'm just going to pause a second for you to see what is happening here. So this was my general formula, CnH2n plus 2. N now has a number sign, it's 1. I'm going to substitute 1 wherever I see N. All right, now what would be my overall formula for methane? So Cn, right, C, 2 times 1 is 2, but plus 2 gives me what? 4. In science, do we really need to write the 1 when we have it in a formula? Out. So the formula for methane then is CH4. Right? And you've been learning about methane from quite early because it's one of the simplest of the organics. So this is my formula, CH4. All right, let's try another one. Ethane, right? So ETH has a prefix, which means that the value is 2. I have 2 carbon atoms present. So I'm still going to use the same general formula because I am looking at alkanes. My general formula for alkane is CnH2n plus 2. I'm going to substitute for N. In this case, because I'm doing ethane, N is equal to 2. So let's go. C, substituting N for 2. H, 2, substituting N again, 2, plus 2. All right, what would be our formula for ethane? My formula then for ethane is C2H6. Let us now look at alkenes. our alkenes, our general formula is CnH2n, right? I like alkenes. Alkenes are easier because you're just doubling your numbers, right? So let's look at alkenes. Alkene CnH2n, that's our general formula, all right? Now, just a disclaimer, right? Just a disclaimer, alkenes don't have any METH, no meth, right? And the reason for that is because alkenes functional group is C double bond C, all right? Now, if I had just one carbon, see there, then I can't be an alkene because an alkene must have C double bond C. So the lowest I can go for an alkene is ETH. All right, just to point that out to you. So the lowest I can go for an alkene is ETH, which is ethene. Can't have METH, can't have meth, which is 1, because the functional group of an alkene, I must have a double bond between 2 carbon atoms. So let's go with ethene, F. So ethene, my N is equal to 2. What will be the formula here? This is butane here. So we're going to have C2, right? Then we're going to have H, and 2 times 2, which is what? C2H4. Great. All right, so we can pick it up a notch. We can go a little faster because alkenes are great. So let's go with propene. So prop is 3, N is equal to 3. So what would be the formula for propene? So I'm not going to go through the whole thing. Tell me what the formula for propene will be. 386. The formula for butane. So we're going to pause here. For tomorrow's class, we're going to continue. So we have alcohols to do formula writing, and we have carboxylic acids. We're going to practice with alcohols and carboxylic acids. And remember, what we are writing now is our molecular formula. All right? After we have practiced that, we're going to jump into drawing the structures for them. So we're stopping here, ladies.